Wow, tēnā koutou, and thank you so much for joining us today. And on behalf of Te Topotanga o Te Whare Koru ki Aotearoa, the Passive House Institute New Zealand, welcome to our next session of our 2026 webinar series. So I am hosting the webinar today. I am a board member of the Passive House Institute, and I'm also certifier for this project for sustainable engineering. So this project is very much about teamwork and collaboration. It's very much a full team effort. So that segues me nicely into this, a quick heads up for our conference this year. The theme being Passive House is a team sport, and that is in Auckland at the end of July. And we'd very much encourage people to come along. We'd love to have as many of you there as possible. And I believe early bird bookings are valid until, was it the 1st of April? I'll get Nikki to confirm that, but I think that's correct. Okay, so just to get some boring stuff out of the way, the housekeeping. So to submit questions, on the bottom toolbar, click More and select Chat, or you can also hold Alt and H on your keyboard. You can type your own question, or if you see a question that you like, you can also give it a thumbs up. We will be recording today's webinar, and we'll send you the recordings approximately 24 hours after we finish, together with the confirmation of the CPD points that you will be getting. Please do keep your microphones on mute and your cameras off during the presentation. If you have any questions, type them into the chat box. As I said, I will read out the questions and we'll go through those at the end. Okay, so moving on to our sponsors. So we are so delighted to have a number of sponsors for today's webinar. We can't really do these without sponsorship, so we really do appreciate it, and we're very thankful for your commitment. So we have three organisations that were involved in this project. We have the structural engineers, Batchelor McDougall, we have Stowe, and we have Allco. So I'll just give them a quick introduction each. BMC, Batchelor McDougall Consulting, they specialise in simplifying complexity. Their approach is to invest time into deliberate early effort while there's still flexibility. And they use smart engineering to give you down-to-earth advice to keep projects on track and drama-free. Allco specialises in waterproofing solutions for both below ground and roofing areas, and they also offer technical design assistance and also on-site support during installation. They have an extensive range of high-quality waterproofing membranes that they've carefully selected from around the world to offer the best waterproofing solutions. And because they have a really comprehensive product range, they're able to recommend the solution that is best suited to your project rather than compromising on the design due to a lack of alternatives. And then Stowe. Stowe is a global powerhouse in building exteriors and interiors, bringing world-class expertise to New Zealand. They live by the philosophy building with conscience, so you'll get world-leading tech paired with a team that actually cares about the footprint that they leave behind. And here are our lovely speakers. We have Rafe Maclean from Rafe Maclean Architects, and he will be speaking first for about 30 minutes. And then Warren, Jason, and Chris will be speaking for 10 minutes each after Rafe. So I will introduce Rafe for starters and get him started, and then I'll introduce each of you other guys as you come up to the mic. So Rafe is a leading New Zealand architect, and he is renowned for his very innovative residential designs. And he leads the Wanaka studio of Rafe Maclean Architects. The studio has pioneered environmentally responsive architecture since it began in 2005, with its work blending passive house with aesthetic excellence, which really sets them apart for against other people in the field. So before I pass on to you, Rafe, I'd just like to very quickly say what excites me about this project. It is definitely a project that really caught my eye as a certifier, and it's extremely unusual, and certainly not the passive house cookie cutter design that characterizes so much of New Zealand passive house design. I can imagine it could have been extraordinarily complex for a less proficient passive house designer, and also with the benefit of a very experienced and committed team that's managed to pull all of these ambitious design features into this incredibly high performing house. So yeah, I'm excited for these guys to show you the elegant solutions that they've come up with for all of the usual passive house problems. And just to mention that we do also have here today Peter Parsons, who's the client for the project, and is also very passionate about this, and has a very clear and exciting vision for this project. So I will pass on to Rafe, and we can get started.
Great. Thanks, Jessica. That was very kind words. Yeah, thank you for asking me to be involved in this presentation, presenting a case study. I chose this project because it's very unique, and it's current, and so I'm up to speed with what's going on, especially around the numbers. So it's relatively easy to talk about. I'm just going to share my screen. I think that should be sharing. Is that all good?
Yes, that looks good.
Yep. Great. Just give me a moment to navigate this. Here we go. Okay. Okay, all set. Okay. So I'm going to talk about the Kauri Trees House. And I've tailored this presentation, and I'm just going to put my timer on. Sorry. So I don't overdo this. I've tailored it for a passive house audience, so it's a little bit technical in places. I've split the presentation up into three parts. Firstly, just a quick introduction to our practice, and then part B would be talking about the site, the brief, the vision of Peter and his site and what he's doing to it, architectural response, planning outcomes, just the spaces, and then part C, dive into the building metrics, the detailing, and then go on to construction photographs of the building under construction. Firstly, practice, Rafe Maclean Architects. We're based in Wanaka. Currently we have 6 staff, all here in one studio. We do pride ourselves on designing, I guess, contemporary buildings that are also very good for the environment, very low energy use, and passive houses is one important tool that we use or we do thermal modeling on all our projects. Not all our projects are passive house certified. Here is an example of some work, some certified passive houses that we've done in the past. So we've just looking through our projects this morning. We've completed 7 certified houses, standalone houses so far, and we've got 3 houses under construction or yet to be certified, and there's 3 houses currently being designed and worked on. And looking at all our work, our portfolio since 2005, around 20% of our work since 2005 has been Passive House certified. So we don't do many projects, but that statistic will improve over time because we only learned about Passive House in 2012. So there's quite a period there that we didn't really know what we were doing. Well, we didn't know what we were doing, but we weren't thermally modeling the buildings. Okay, the Kauri Trees House, Part B. Talking about the site, is located around about an hour's drive south of Dunedin. So there's a map showing Dunedin and Kauri Trees House. And this is a view from the site. Probably almost day one when my first visit to the site. And the house site is just on this knoll here. So this is a view looking east. So there's a very distinct ridge line going down the site. And yeah. About the climate of the site, this is the extracted from PHPP on the climate data. So it's been altered for the altitude. Altitude is 182 meters above sea level. Interesting thing here is just the exterior ambient temperature. So in peak of summer, it averages around 14 degrees on average, and then in winter around 6 degrees. So quite cool environment, quite close to the sea. And this picture here just shows just the sun pathways. Often do this in the first visit to site, just to get an idea of where does the sun come up, where does the sun set. So this is looking east, so that's where sun rises over the sea in peak summer, and that's where it rises in winter. And then looking towards the west, up the ridgeline, that's where the winter sun sets around about 4:30, and then around 9 p.m. midsummer. In 2004, that's when we were approached by Peter we were asked to be involved in the project, and Peter's initial brief was around 18 pages long. So I think it was probably the longest brief that we've ever received in terms of content and requirements. So this is just, I guess, just the basics that from it, looking back at what most important things. Certified passive house. Yep, we could do that. Earth sheltered. Well, we had to sort of find out a bit more about that, what that meant. Architecture award winning. We try not to talk about that too much because it's sort of you can't really anticipate that. Concrete construction. We had some experience with concrete before with precast panels, so we knew the language. At that particular time, I just returned from a trip to Japan, and I experienced some wonderful architecture over there using in situ concrete. So I was quite excited to sort of read this and go, okay, I know what Japanese can do with concrete underground, and so that was it made me smile. minimal engineering challenge. That was, we're going to test that later. Grand Designs candidate, that's quite interesting because Grand Designs are filming the project now. Wasn't planned from day one, but they're on board. And then future heritage listing, that's out of our control, but we'll try and do the best building that we can. And also, yeah, off-grid, totally off-grid, no rain, no water supplied to the site, so rain harvesting only, and a request for it to have a very long design life. About the site, this is, I guess, a key driver for the project is Peter's vision for the site. So this is an extract from the Kauri Trees website. Address is up there, and I'll mention it later again. But it tells you, this website tells you all about Peter's vision for the property, and the main vision is that he would like to establish the southernmost Kauri forest in New Zealand, and that he's started by planting thousands of nursery trees, and then slowly this year they're going to start planting Kauri trees, which have been propagating in a nursery nearby. And this is a picture of the site, boundary there, and this is native, existing native planting in the valleys, and this is pine plantation surrounding the properties. And the site for the house is just up here, on this little knoll here. Concept for the project. This is just a quick sort of overview of basic concepts that we sort of started with. This is a map of the property of the site. There's the line of the ridge line coming down here, and there's sort of three ideas that I pulled into the project. One is to how do we have a sort of an underground building or submerged building that captured the sea view over here to the east, but also not be totally underground so we can't get any daylight. So the idea of having a C-shaped building, hugging the ridgeline, so following the contours around. And we talked about having courtyards in the building for shelter from the wind. So this C-shape here formed its own natural courtyard in the middle. So it was a good start. And then also thinking about this idea of how do we insert spaces into the ground and have livable spaces that we can bring light in, we can see out to the view, and uplift the soul, etc. And thinking about grafting spaces into the land, how do we sort of insert them in under the soil? And the third idea is the idea of the tree canopy eventually growing up, and we've got the canopy, which is, we could symbolize that as the roof, and we've got the structure of the trunk and then the root system, and this, the shape of the trunks, the structure of, how do we hold this canopy up? So there's a few things going on there that we had in mind when developing the plans. First concept idea was to, we've got the C shape going. This east out here, and basically when you approach the site from above, the building sort of is camouflaged because the ground's been lifted up and the spaces have been inserted underneath the ground. Almost like the word grafting came up a few times. So that was the first crack at it, just to see how the spaces could work and what sort of scale this building was going to be. And that idea was developed a bit more We lifted the roof edge up when we started to think about the practicalities of someone climbing up onto the roof and falling off it, and trying not to have barriers. So basically made sure that the roof was more than a meter off the ground, so no one could climb up. So that was the barrier. We looked at green roofs, and because we're rain harvesting off the roof, we looked at the calculations about the rainfall. Taieri Mouth gets about just over 500 millimeters a year of rain, so not much. So we worked out that the plants were actually going to take too much water from the roof to grow. So we pulled this back to having just ballast only, and then reintroduced planting as we got an idea of how much rain is actually falling on the property, and servicing underground tanks, which serves the house. Floor plan. So this is the thermal envelope. Just draw this with my mouse. So that's the house. So we've got 2 bedroom or 3 bedrooms, kitchen space, the big window to the northeast, living space here. My laser pointer. Living space here. Main bedroom, ensuite, laundry, and a back entry, main door here. And this is where you enter from, coming down the ridge line. You come in into this, come down into this courtyard space, and from here you can look right through the building to the sea. And then this area here is basically that's the garage space. So that's unconditioned space. So it's not insulated at all. Roof plan. So there's the outline of the insulation on top of the conditioned space, and we've got 3 roof lights, and over here we've got the outlets to the underwater tanks. So the water falls on the roof and drains to these points. And just quickly, I'll just touch on the sections so you can sort of get an idea of these are underground water tanks, and 1.5-degree slope, around about 3.1 ceiling height at this end, at the high end, and about 2.6 I think it is at this end. So quite high ceilings. And we've basically inserted in the building but then pushing the earth back. So when you're in the kitchen space or inside, you get the feeling that you're underground or partly underground. And some sort of late documentation stage renderings just to get everyone excited, especially with the mature Kauri trees. So we're sort of projecting in a few hundred years into the future. Yeah, so it's a view from the east. View from the north, southeast, I think it is. Yeah. Actually from the northeast, sorry. And that's a concrete roof, and we have got these curved buttresses that hold up the roof, and playing on going back to the concept of that shape of the trunk going up to hold the canopy. So yeah, all this is all in situ concrete. The roof, these are precast buttresses, and then over here, which is part of the thermal envelope of the wall, that's a stow plaster system over insulation onto a concrete panel. and that's a view from the western courtyard. So you come down the steps, and you've got a view right through the building to the sea beyond. Onto the building metrics. I'll just run through these just because it's really important for this audience. Treated floor area, 150. Footprint, 182. Compactness of the building is 4.3 per square meter of the treated floor area. That's quite high. We tend to, anything under 3 is much easier to design for. So that was quite challenging dealing with that, and it's because of the C shape. Heating demand, we're under that 15 because this gets rounded down to the whole number. Frequency of overheating, very low at 1.29. And target pressurization, this is a blower door test. We've inserted 0.3 into the calculations. And just we comment on that is that we've been putting 0.3 or 0.35 into our PHPP at a pre-construction stage, because what we find is that if we put 0.6 in and the airtightness test comes back at say 0.15 or 0.2, it's a huge shift, and we find that overheating jumps up really a lot because of that. So if we go in at 0.3 or 0.35, if there is a shift, it's not as big. And we're finding that 0.3 or 0.35 is not too hard to obtain now. A few years ago, it was quite hard, but now with the contractors being more skilled at it, we're getting better results. And as I comment on the specific heat capacity, which is the thermal mass in the building, this is the highest it can be in PHPP, because the floor is concrete, the walls are concrete, and the roof is concrete. So we use that. That's the first time we've done it that high. Using Design PH, which is the SketchUp plugin for PHPP, was really useful in this project. And just because of the shading from these buttresses, very hard to sort of manually sort of calculate those. The red is the thermal envelope with the windows, and the grey is the self-shading of the building, so overhangs, buttresses, and there's a garage over here as well. Beyond this is the site shading, which is the surrounding hills. Just another view of the Design PH model. Jumping into the makeup of the building, because all the material, all the envelope, it's all the same material. These are very simple compared to, say, a timber frame building. So the floor here, we've got basically 100 mils of concrete, and then 500 mils, half a meter of EPS insulation. And then the roof, we've got 180 millimeters of reinforced concrete, and then 300 millimeters of PIR, which is it's got an aged derating factor in there as well, and then the membrane on top. And then two wall conditions. One is to air, and then another one is to ground. So to air, we've got the concrete panel, which is precast panel, 200 millimeters of EPS, and then the stow plaster system. And then underground, we've got concrete, EPS, and a protection sheet. So very, very simple in terms of the envelope makeup. Just going to talk about, just cross this one out here, just talk about this detail at the bottom here first, which is the foundation. One thing we work with a lot is the thermal bridge software. we use Flexo, and we used it a lot in this project to optimize the detailing. So, and also working alongside the structural engineer, especially around the bearing capacity of insulation, and making sure that it's going to work for them and also work for us, and also working with the in this case Allco, with the flooring, the tanking membrane, and then its junction to the stow system on the walls. So quite a complex detail, which had quite a lot of iterations just to get right. Now, for example, here we've got the platinum EPS on the outside, which Stowe had to be happy with using, and also Allco had to be happy using as well. And then underneath we've got Slab X EPS for the bearing capacity underneath the foundation, and then there's this 500 mils of I think it's just S grade EPS over here. So you can sort of see from the this is from excerpt from Flexo, and this is the sort of thermal characteristics. And what we're trying to do is make sure that the internal surface temperature on the corner is 17 degrees and above, ideally. This one is 18.8 with 20 degrees inside and ground and air conditions outside. So quite a team effort on this one just to get that right. The eaves are particularly sort of special, unique. We've got I'll try to explain this. We've got a concrete roof here, and it extends out to form the eave. And to make this thermally efficient, we've put a thermal break here, and of course that needs to hold this eave up. So we've used a balcony connector, which in Europe is typically used for balconies outside of apartments. So this is imported technology. This is a picture of one system here. And you can sort of see over here, these thermal pictures, is that without a connector, you can sort of see the lines here and internal surface temperature just in there of 16 degrees. So it's a bit of a cold spot right there. And you can sort of see how that's working. And then with the connector in there, this internal temperature jumps up, and it's quite a smooth color, going right around, which is fantastic. The conductivity of these aren't that great. It's about 0.13 from memory, which is about the same as a piece of wood, but it's got the strength to hold both sides, or hold the balcony up, hold the eave up. So sleekness was quite a task, because we had to get the BMC, the structural engineers, comfortable with this system before we could specify it. And then the windows, we used InnerSign windows from Eco Windows in Hamilton, and the uniqueness of these are they've got very low UF value of around 0.58, 0.6, around that value. And we also took the insulation over this is a plan detail here. This is the exterior, took the insulation over the face of the window. And working with Stowe, they do this in Europe quite a lot. So working with Stowe, the plaster comes on and just finishes against the window face there. So by doing that, we actually got a negative thermal bridge coefficient here, which is a first for us. And just there's some details here just showing how the insulation comes over the frame. And this is the head detail here. So we drip edge just there. And roof windows, first again for us, working with Eco Windows, we found a window that would work from Velcro, and yeah, designing it along with the engineer and Allco, the membrane people, how this would work, and then thermally modeling it to make sure it works for us. was quite an exercise, things that we sort of learn through the Passive House course, but don't actually do in reality. So they're quadruple windows. And jumping into construction photographs. So this is almost, well, probably near close to day one. You can see the nursery planting here happening on the site. This is the public road going past, driveway, and this is the site. Well, the site's just here actually. This is the driveway being formed. Being off grids, Peter and got the solar array installed quite early, so the builders can use the power off that instead of using a generator. So that's quite useful. And I'll just run through these photos. There's quite a few of them, so quite quickly. Foundations going down. That's the slab X insulation, I believe, that goes underneath the panels. Picture from the precast panel place in Invercargill, along with Grand Designs filmer. Panels going up. And the curved buttresses at the factory, Stress Creek in Invercargill. That's the name of the prefabricator. All the slab insulation installed. And these are pictures from yesterday morning. So this is the first buttress being lifted into place, and there it goes there. And that's a picture from the end of the day. So we've got all these buttresses installed, and there's a gap between the buttress and the wall so the insulation can go past and still leave a gap for maintenance. I think there's about 300 mil gap there, so there's about 100 mils gap between the back of the buttress and the stow plaster. Yeah, and this is the project team. So myself, Amanda, and Nicole worked on it. BMC, Sustainable Engineering and Certification, Stevenson Williams, the builders from Dunedin, and that's the website for more information about the site. And of course, our key suppliers, Stowe and Allco. Thank you.
Fabulous, Rafe. Thank you so much, and you're spot on time. Well done. Yeah, I mean, you can just really tell with your slides that this really is black belt passive house design. This isn't you know, for the faint-hearted. So you know, the whole team should be very proud. So hopefully some people have got some burning questions for Rafe, but we'll move on to Warren now. So yeah, I think you can see my screen. Can you? Are you able to see the speaker's screen? Is that what you're seeing? Yep, brilliant. Okay, all right. So just to introduce Warren. Warren's the principal engineer with BMC in Wanaka. He's a chartered structural engineer with more than 13 years of experience in New Zealand and 38 years overall working in numerous engineering roles, including in the UK, doing management of construction and maintenance teams, large-scale civil projects, and also a former director of a UK consultancy. So he's currently undertaking projects in residential, commercial, seismic assessment and strengthening, and civil and industrial civil structural design. So there's quite a lot of expertise there. During his time in the construction industry, Warren has had experience in designing temporary works, project programming, budget control, procurement, health and safety, and personnel management. He's also acted as a party wall surveyor, a temporary works coordinator, and an in-house quality assurance officer. He's a chartered engineer from the UK and regularly attends continuing professional development seminars and meetings as a member of ENGIE New Zealand, ISTRUCT-E, and NZGBC. And through his initial education in architecture, Warren has had a long-standing interest in energy efficiency and is a Homestar version 5 designer and assessor. And so we're delighted to hear your perspective on this fabulous and potentially challenging structurally project.
Thank you. So the initial brief came through and we were all aghast at the design and really wanted to get involved in this. There were a few things that we needed to run through, really, the different types of options that could realize this vision. So we had a look at the roof, and there was a number of different alternatives. But what really drove us was the briefs for the in situ concrete. It was going to be the more exacting process to do the analysis of, but you know, the client had a feeling that this was the right movement to go into. So when we first had a look at this, we just decided to have a look at it as a slab spanning over the whole of the structure. And we had a continuous concrete slab all the way over. Now, there was a couple of different things we had to look at here. So for the initial stages, we did a quick two-dimensional analysis of the roof of the structure, going across the width to determine what the bending moment profile was going to be over each point and support. We knew that the central core area would need some form of an additional support there for it to work. And this is where we determined the loadings that were going to be on those spline beams, effectively, of the internal walls. And then we could determine from that what we were going to, what type of depth and detailing that beam was going to require to stabilize the structure. So to give you some idea of what the deflections criteria is on the building, the central area around where the three, but in the central area, you can see what the deflection is. And we've exaggerated this just to prove what the problems were there. So we've got the green lines are effectively the supported edges of the PC panels, and the purple is in the center. But during that process, Rafe came to us and said, "Well, I think we've got to do something different with these overhanging canopies because of the thermal modeling that he'd done." So then we looked at the cantilever connectors to see if we could utilize them. So from the initial model, we knew what type of moments were going to be at that point, and we had to try and match up the components that were on the market, although a far removed market, to see if they could provide the restraint that we needed. We do have a little bit of support afforded to the system from the PHINZ, but not too much. They're more of a secondary support, really. So if we just go back a little bit, right? So the foundations. we had good ground, and it's a very stiff clay up there, with some areas that we had to do some fill within the garage. And of course, if you've seen the sky photographs, the aerial photographs, you can see that there's quite a little nest of props splaying out from the external envelope. So we always needed those in place as well, just to stabilize it during the construction period. But it was the foundations that we had to have a quick look at. So what we do from our model is we determine what the bearing resistance, the design bearing pressure is underneath the walls. So when we get a capacity for the ground, in this case 300 kPa, we have to then look at what pressure is being imposed on that, and then what we use is what the bearing capacity we've got left, we've got to take off and the compression within the insulation. So because each insulation has a rating, and so what we try to do is determine what form of deflection would be provided from each of the installations, then that add on to what residual capacity we have from the foundations and the geotechs. So generally we try to go for obviously the one with the highest compression resistance, and some of the Expo insulation has a compressive capacity at different percentages. So what we try to look for is the 1%. So for 100 mil of insulation, we get 1 mil of deflection. And most of the building codes and the bearing capacities are based on a 25 mil overall deflection. So when we prorata our design loads from that 300, we have a residual compression that we can take in the insulation so that we meet the overall 25 mil requirement. So that determines our specification for the foundations insulation, but we still had to make this thing work. So there's lots of different pressures on this building that we've got to take account of. So after our 2D initial sizing, then we knew we were going to get somewhere around the correct profiles. We had to do a more rigid analysis, a rigorous analysis, sorry, using the ETABS model. So the roof effectively becomes a rigid diaphragm which all the walls are connected to, and it distributes all the lateral loads around the shear walls around the perimeter and internal of the building. So when you go back onto this one, you can see for each different direction, going towards the east and towards the north, we have different areas where we're in compression and tension within the concrete slab. And what we have to do is determine what the stresses are in each of these zones, and then increase the reinforcement from mesh to be able to cater for those loadings as well as the gravity loadings. So it's quite a maze of work to do. I think was finished. Oh, so you can see on this outlet, you can see some of our analysis package shows us what type of forces are then going to be imposed onto the PC walls, and then we can design those and the foundations and the connections at top and bottom to be able to realize those capacities. And I remember right at the very beginning, we'd done all of the we'd done all of the panel walls, and then Peter came back to us with these little bas relief areas around the building. There's 3 of them, and he determined that he wanted that to be, well, I think we advised that 50 mil was probably the deepest we could go to with those. But then we had to look at our analysis for these panels and then made sure that in the residual 100 mil thickness of the PC wall, that we had enough strength within that area to cater for the loadings that were imposed on it. So it was, I mean, you can see there the notch that's got there for the thickening that goes over the core areas of the wall. And that completes my presentation. Thanks a lot.
Wonderful. Thanks for that, Warren. Good to see that, you know, the depth of investigation that goes into this kind of project. Okay, so now we are going to go to Chris. So Chris is the senior product specialist for Allco. He has very in-depth experience in the construction industry with over 20 years of experience as a draftsperson, liaising with architects and engineers, builders and contractors in the industry. He has a vast skill base, and he assists the sales and QA team, providing technical support across their products, from assessing geotech reports to reviewing project documentation and producing site-specific CAD detailing and specifications. And he is going to bring his experience to this project.
Hi there. Hopefully get the share screen to work. Sorry. Hopefully you can see that on screen now. Right. Thank you for the invitation, and thank you to all the team for inviting Allco to be part of this unusual project. Nice to be part of something different. Allco, as it says there, we've been around for 50 years as the name Allco, but in the more recent time, a lot of people know our Volclay waterproofing system, and I'll talk about that, how it's been detailed into this project. Something that we do differently to a lot of membrane suppliers is that we have a team that goes around the country verifying that the systems that we say are suitable for a project are actually being installed properly, which is a little bit unusual for a supplier. And I'll just start by sort of covering the areas that we supply products for. Right across the building envelope, but typically based around membranes, from green roofs, warm roof systems, across the balconies, car park membranes, and down where most of our business is below ground. So that's our Volclay system for being pre-installed perhaps onto precast panels, or laid under in situ concrete slabs. Lift pits is one of the mainstays of our business, because of course that's the lowest portion of your building usually, and has no drainage in most cases. We do a number of systems, and as you mentioned at the beginning, they are distilled from around the world to achieve certain things for certain purposes. So we don't sell sealants, we don't sell products which are outside our quite limited scope. And what that achieves us is to be very specialized around those and provide better support to our clients, and thus their clients providing the best solution. As in this case, it is of course the best solution. Now, when we were approached about this job, it was not, didn't come across as unusual. We detail a lot of waterproofing products, a lot of to have a waterproof building. Now, what we'd normally see is perhaps an architect coming to us and saying, oh, I've got a very high water table. I want to protect my structure from rising groundwater. Now, in this case, when Rafe came to us, it wasn't so much about, hey, I've got a problem that I need to solve. It was, I've got a building, I want to increase the durability for that structure that's in the ground. There's moisture in the ground. How are we going to protect that? How are we going to detail all of these junctions? How are we going to detail a membrane that will protect the main concrete structure, as well as providing some protection to the insulation? Now, insulation in this case does have the capacity to absorb water. So we've got to detail something in there that's going to protect that. So it's going to be acting as insulation as optimally as it possibly can. So that's the portion in ground. So we're protecting that concrete, adding durability to it, and we're using our Volclay bentonite membranes. Now, bentonite is volcanic clay, so it's a natural material. But the aspects of that is that it's a self-healing, self-sealing membrane. So let's say a construction worker's wandering around on top of the membrane, he punctures it. Not a problem, because when that concrete for the slab gets poured on it and moisture starts to swell the membrane a little bit, the puncture that was there now seals. So one aspect of it's a very, very robust membrane. Now, the roof system that we've proposed here is our all-therm warm roof. It's got a TPO membrane over the PIR and over a cover board. Our system for our warm roof is a little bit different to some others. It does have a cover board, and that cover board just distributes some of the load across the PIR. Now, some of the systems that don't have that, when someone's wandering around on top of the PIR, it's actually forming indentations. Now, when you put a membrane over those indentations can transfer through to the membrane, not be quite as aesthetic, but as Rafe has mentioned, in this case, we're actually using a ballast over the top of the membrane itself. We do provide a drainage layer between the ballast and the membrane, and that has a filter fabric built into it to filter any small things that will come through. Now, of course, in this case, we needed it to be potable water certified, as we will be using the water to drink for the property. A couple of specific aspects in the foundations, as I mentioned, the Volclay system. And something that Allco do, and myself specifically, is we do specialized details that match, in this case, what Rafe was indicating in terms of the structure, the insulation. Our detailing then needs to match specifically. So we're not going to just say, here's our typical details. This is not a typical building. So therefore, we need to match it up so that the council and everyone is seeing that we're all on board and we're providing a system which is going to function properly. Now, the Volclay system has two membranes. On the left, you'll see the Voltex, which is I describe as a carpet. It's actually sitting underneath the precast panels in this case. And on the detail on the right-hand side, you'll see it's transitioning across to the in situ slab that's going to be poured. Now, Voltex itself has fibers on the back of it that will bond with that concrete, and it will become a monolithic part of that concrete. So you cannot pull it off. It's not like putting perhaps a bitumen layer underneath your slab. This is part of your slab. The secondary membrane that you will see in the green on the detail is our swell tight membrane, and that's a post-applied membrane. So once the panels are up, and we saw in Rafe's photographs, they are all up now, and we could actually see the swell tight being applied to the back of the panel, and there will be a protection board put over that. Now, you'll see the Voltex in this case sitting actually in water, but that doesn't matter. The geotextile fibers will hold the bentonite in there, and won't be an issue, and it will then be pinned up to the back of the swell tight and form a continuous waterproof barrier. Now, on the right-hand side of that detail, you'll see that on the outside of the insulation, we've got another layer of membrane. Now, that's our Casali DPM bitumen membrane, so it's providing a moisture barrier to that in-ground portion of the insulation. So as we know that insulation, once it gets wet, it does reduce its performance slightly, so we've provided that layer to protect it from that. And of course, we're transitioning up the wall into the Stowe plaster. So again, collaboration. Stowe are actually testing the bonding strength of their plaster systems onto the back of our Casali. So we're working in tandem to get that sorted. And the all-therm warm roof system. We should hopefully know what warm roofs are now. So we've got a vapor barrier that's, in this case, sitting on top of an in situ concrete substrate. Then we have our PIR, nominally at 140 mil thickness. It's giving us an R value of 6.6. Then we have the cover board on top, and then the membrane on top of that. So in this case, it's a fully bonded system. There are no mechanical fixings, so we're not getting any thermal bridging across. So it's an optimum design. Now, on top of the membrane, of course, we'll have the aquadrain, which is a plastic cone system for the drainage void under that, and then a filter fabric that sits on top of that, and then the ballast placed on top. Okay, so what that's actually achieving is from a durability point of view, it's a protected membrane system. So while the membrane can be exposed to UV, if we're placing a ballast over the top of it, it's actually providing that extra durability to that system. So we're not having to worry about that after the 20 years that the product is warranted for. We've actually protected it from the elements that are going to degrade it anyway. So we're actually building a much better system than we would specify as a standard system. So in the basement, on the ground, you've got the Volclase system, which is a natural material. Then you've got the TPO membrane on the roof, which is being protected from the UV by the ballast. So all in all, a robust set of membranes providing specialist systems across the in-ground and roofing systems. But I have to say it was nice to be approached about a project where the first question was not perhaps cost, but actually we want the best that can be provided, because this building is going to be an iconic building that is going to stand the test of time. So will your membranes help that situation? So it was very nice to be approached. And that sort of rounds it up from my end.
Wonderful. Thanks, Chris. That was for me, that was really great to hear about those natural self-healing membranes that you're using with the bentonite. Very, very cool.
Thank you.
Okay, so I would just encourage anyone, if you've got any questions for any of our speakers, to pop those in the chat, and then we can go through those at the end. Otherwise, it's just going to be me asking questions, which is fine because I've got lots. Okay, so just to finish off now, we're going to hear from Jason Wanden at Stowe. He's another very experienced team member with over 30 years in the architectural specification and construction industry, and with practical experience across all those sectors. He's got 15 years of project management and product evaluation experience with brands, and he's developed skills in product development, testing, consulting, compliance, and quality assurance. And for the last 8 years, he's been working as the senior technical manager of Stowe, and he assists Stowe regional managers with the delivery of their render systems to architects and designers, and supports them with the design and compliance process. So I will hand over to you now, Jason.
Thank you. Sorry, give us 1 second. Perfect. So everyone can see the presentation okay? Thank you. Okay, yeah, like Chris, we love being involved in these sorts of very unique projects. So thanks for the opportunity to come along today and just give you a quick spin through the Stotherm exterior insulation system, focusing on passive house design. Stotherm system itself is a multi-layer system, starting with your concrete, your masonry structure. We adhere insulation panels. They can be EPS or Rockwool, being the two most common. We fully bond those insulation panels to the concrete with an adhesive render and supplement that by installing mechanical anchors through the panels themselves as well. Once the insulation is installed, the full system is covered with a base coat render, in essence, to level the surface. Following that, our Stow Armat synthetic reinforcement render, it incorporates a fiberglass mesh, is laid over the top. And then finally, the system is finished with any of our range of Stowlit coloured finishing renders and either a facade paint or a Stow clear coating. The most common insulation materials are obviously EPS and Rockwool, as I mentioned before. On this project, Rafe specified the graphite infused EPS, the platinum board. 200mm thick platinum board achieves an material R value of about 6.25. Now that's the insulation value is directly relative to the thickness of the insulation material. So you can sort of see there, if you were to specify 300mm of graphite infused EPS, you can get sort of over 9. There is really no maximum limit per se in terms of insulation thickness. Apart from Rockwool, Rockwool is limited to 100mm at the moment from a render perspective. So why external insulation systems for passive house? 3 key features of the Stotherm external insulation system for the Kauri Trees House. Thermal bridge elimination. Rafe's mentioned that already, and I'll talk about that a little bit further in a minute. Assisting towards the continuous insulation layer principle, so connecting wall insulation with foundation insulation and also your roof insulation, and taking advantage of the thermal mass. So one of the key design considerations mentioned by Rafe was the elimination of thermal bridging through the building envelope. This is especially important at joinery openings, and Rafe presented a couple of his details there. The details on this slide and the thermal images are taken from the Cement and Concrete Association Code of Practice 2022. And they're an excellent way of trying to better understand heat and moisture transfer within the building envelope. The construction detailed on the left has internal insulation. It's a concrete masonry wall, obviously. And it highlights the potential for thermal bridging through the joinery to wall junction. The construction detailed on the right, which mimics the installation detailing on this project, demonstrates the elimination of the thermal bridging through external insulation and consideration of that joinery to insulation junction. Another key area or potential area for thermal bridging is actually the mechanical fixing of the insulation material itself. The image on the left-hand side is a face-fixed anchor. Anchors typically are plastic. They are embedded into the concrete masonry structure. And when they sit on the surface of the insulation, they're able to transfer or bridge that heat directly through the fixing underneath the render system. Now, what that does is, I'm sure everyone's probably seen it before on cold mornings on good old EIFS buildings, leopard spotting. You can sort of pick out where every single insulation fixing is. What that does is that over time, that can have that can permanently change the appearance of the render finish. We avoid that by using our Stotherm recessed anchors. In this situation, the anchor is actually countersunk beneath the surface of the insulation material, and the anchor itself is then protected or covered with an insulation cap, offering like a thermal break. So here's the sort of 3 photos showing that process. First photo on the left-hand side is the anchor after it has just been installed. It sits approximately 15 to 20 millimeters beneath the surface of the EPS in this case, over which a cap is installed. Now the cap ends up finishing flush with the face of the insulation material, which leaves us a nice uniform surface for the render finish on top. Continuity of the insulation layer is again really important for the avoidance of heat loss and eliminating sort of those internal dew point locations. Again, these details are taken from the Cement and Concrete Association Code of Practice, and they demonstrate the distinct difference between internally insulated walls and external sort of full envelope insulation. The construction detail on the left demonstrates thermal bridging through the wall slab and cold temperature on the interior face of the concrete wall behind the insulation, which can lead to condensation and mold. The construction detailed on the right again mimics the installation detailing on the Kauri house, and it demonstrates the continuous insulation principle, eliminating thermal bridging and pushing the dew point to the exterior, just probably within that insulation layer. Stow render systems themselves, insulation is great. However, your wall structure still does need to remain vapor permeable. Stow render systems are very vapor permeable. They will allow the wall structure to breathe and not retain any moisture within the wall assembly. The render systems are also incredibly weather resistant. So not only are we allowing vapor to move through the wall, we're also preventing rain and wind-driven moisture from getting into the structure itself. The Stow Armat render system, it's our sort of jewel in our crown. In essence, it delivers 3.5 to 5 millimeters of vapor permeable waterproofing on the exterior of your building, not just reliant on a coat of paint or an acrylic texture. You actually have a really robust weather-tight layer. It provides, they say, 10 times the fracture resistance of a standard sort of cement-based plaster. It's incredibly flexible and has excellent impact and abrasion resistance. So just to summarize the benefits of the Stowtherm system, we can take advantage of the thermal mass. So the thermal mass and heat retention capability of the masonry wall is fully utilized. The building facade, if you like, is protected from heat loss and gain, and dew points form on the actual outside of the structural wall within the insulation layer, not on the interior surface. And incorporating things like our Stowtherm anchors and consideration around joinery, connections, etc., we can eliminate thermal bridges and contribute to that continuous external thermal envelope. And from our perspective, sales and technical support, we pride ourselves on sort of the sales and technical support we can offer designers. We really love being involved in projects from an early stage. Sort of like Chris mentioned before, the earlier we can get involved, the more assistance we can provide to make sure that the Stow systems are implemented and incorporated within a project, such a way that it works for us and also for the end user. You can contact us via our website. All contact information and a whole bunch of details and all of that are available on there, and happy to work on specific details, as Chris mentioned before. So thank you.
Wonderful, thank you, Jason. That was fascinating, and so good to see a supplier dealing with integration of insulation and weatherproofing as well, and taking into account both of those things. And those the Stowtherm anchors look like a very, very clever solution. Wonderful. Okay, so I will move on to the Q&A. So we do have a few questions. We don't have a huge amount of time. We've got about 15 minutes. And if people do need to go at 2, then you're welcome to, but we might just overrun a little bit to try and get through some of these. So first question is from Nigel to Rafe. Did you consider a more northerly orientation?
Thanks, Nigel. Yeah, it's a tricky one because the site was sort of angled that way towards the east, and that was the main view. So definitely had that in mind most of the time. It's like, well, north's up there. How do we make the most of that? So yeah, so opening and closing those apertures to the sun to the north as much as possible was key. But yeah, ideally more to the north would be better, but on this particular site, it just didn't quite work with the topography of the land. Yeah.
Okay, and a question from Richard. He's interested to hear a bit about the MVHR and hot water systems in the building.
Sure. The MVHR is a Zender system, Q350, and just quite typical of our projects. Air conditioning, there we have allowed for air conditioning into the house. I don't think we put it in PHPP because we didn't need it, but it's there as to retrofit, so the pipe works, all the conduits are there. And then the hot water system is something I didn't talk about, is very unique as well. We're using a thermal battery, which Peter investigated and researched, and it's coming in from the UK, I believe, made by Sun Amp, and it's a Thermino X Plus system. So how it works is, this is how I believe it works. It's like a box of stuff that you charge up and heat, and then it heats the water from that for your domestic hot water use. In terms of energy used, it's not terribly efficient, but the benefits come from its storage capacity. So it's very, very low heat loss. So it's got amazing storage capacity. So you can just plug it into the wall, so direct electricity, or you can hook it up to a heat pump, which then you get the COP advantage. So I think in this case we are going to use a heat pump system to heat that thermal battery to heat the domestic hot water. So yeah, and yeah, that's all. Yeah, that's
Oh, okay. This is probably a question for you again, Rafe, but maybe also for Jason. Did you consider insulating internally?
No, because the dew point would be in the wrong place. So there's always going to be insulated on the outside. Yeah.
Yeah, agree.
Cool. And for Warren, were there any specific issues with those continuous balcony connectors?
Not really. Once we matched up the bending moment capacity of our model to the capacity of the connectors, and there's a whole range of them in there for different types of installation. It was really more of a setting out process, because they come in meter and 500 mil lengths. So we had to go around the perimeter, set them all out, and then got some direction from their technical services department about how we would make up the makeups in the middle, and we just put some PS in there locally.
So how tricky was that for the builder to
yes, they've only just arrived in the country, and we will find out soon.
We'll find out. Yeah. Yeah, shout out to the builder. It looks like a fantastic project to work on. Okay, where have we got to? Chris, what warranties do the various membrane systems have?
Below ground is 20 years, and above is also 20 years. So nice simple answer.
Nice and easy.
Durability wise, roofing membranes need to have 15-year durabilities. because it's under a ballast, it is accessible from a servicing point of view. Below ground membranes need 50-year durability because, of course, we can't get to those.
Yeah, understood. Jason, where's the graphite EPS made, and and what aging data do you supply? So I might just jump in there to say that the EPS generally doesn't need age data because it ages instantly the second it's manufactured. So it's not like XPS or PIR, which loses its performance over time. But where's that made?
It was an X-Pol platinum board that was specified for this project. So one of the X-Pol plants will be manufacturing and supplying the product. They all manufacture to a pretty consistent thermal conductivity. So you have good certainty around thermal performance based on the thickness of the insulation material.
Cool. And Stephen, wondering whether there was a consideration for precast sandwich panels.
Yeah, I think we started off with that idea. Precast sandwich panel usually is 150 of concrete, then 50 mils of XPS, and then another 50 mils of concrete on the outside. It just wasn't enough insulation to work, so we had to think of alternative solutions for that.
Yeah. So driven by the U value requirement.
Exactly. Yeah.
Yeah. Okay. So from Rowan, Jason, are the recesses for the wall for the insulation anchors manufactured into the product, or is it done by the team on site?
So they're actually applied as an EJOT fixing, and it actually has a specific installation tool, which in essence is a plate that fits into any sort of power drill. Is a plate with a cutting portion on it, which is the same size as the washer, if you like, the Stothem washer. So it's a one process. You pre-drill a hole, obviously, into the concrete through your insulation into the concrete, insert the fixing, apply the tool, and as you screw the anchor in, it is at the same time cutting the insulation and compressing the insulation behind the fixing head. So there's no removal, if you like, of the excess insulation. It gets compressed in behind the washer, and yeah, then in essence the cap just goes in over the top.
Very clever.
Very clever. Very clever.
Stephen says, with the interior concrete finish to the ceilings, it would be interesting to know how you're dealing with services runs.
Yeah, we do have a drop down, a bulkhead ceiling in places to run the ventilation ducting across the living areas between the two areas. Yeah, so very carefully. I mean, it was worked out quite early in the design. You know, how do we get services across the building without sort of affecting the exposed concrete visual. Yeah, and then minimal conduits for the electrical inside the concrete and the roof. Yeah, so
including some sprinklers as well.
Oh yeah, sprinklers. Yeah, and fire sprinklers. We've got fire sprinklers, which yeah, we're carefully laid out in consultation with the engineer. Yep. It's quite funny because nothing's going to burn in the house, but to minimize the static firefighting supply, if we put sprinklers in, we can drop the tank size right down. Yeah, so a little oddity there.
Yeah. Richard says, do you have a general fix on the thermal mass latency with respect to the heating or cooling of the building?
I think yeah, specific heat capacity, which is on the first page of PHBP. I think I played around with it one day, and you know, if we didn't have that thermal mass in the building, it would definitely perform differently. It definitely stops the ups and downs of temperature fluctuations, and that's how deep we went. We didn't go any deeper than that, but maybe Jessica, you could comment on that.
So would you say that the building requires less heating and less cooling as a result of having such high thermal mass?
Yes.
Oval?
Yep. Definitely.
Yeah.
Yeah. I think there's going to be a startup period where it's going to have to sort of take a while to sort of build up to a nice level, because of all that thermal mass to bring up to a certain level. But after that, I think it's going to be quite even.
Yeah. Oh, yeah. As you said, quite unusual for New Zealand projects to have such a lot of mass in them.
Yes. Yeah.
Okay, that was the last question. So we do actually have a couple more minutes if anyone has any last minute questions they'd like to add. Let's see, is there anything, since we've got a couple of minutes, is there anything that, oh yes, Rafe and Warren, would you say that the concrete construction made the airtightness strategy easier or harder?
I think it's going to be relatively easy, because there's less junctions, right? So I think it's just going to be around the windows really, because everything else is pretty well sealed. We do have a couple of sliding doors, which will be red flags in terms of the into sliding style. But otherwise, I think it's going to be a good result. But I'm always optimistic about these things, so we'll see.
We do have some joints between the PC panels in some places that at the moment they've got some PEF rods in there, and then they're going to just mastic over it, I think. But I guess that would be the area we'd need to an additional look at, was the windows.
Yeah, there won't be any pre-lining and testing as well, so that's quite interesting.
Yes.
Yeah.
Yes. So a bit more pressure.
Yeah.
Yeah, but a very experienced builder by the sound of things.
Yeah.
Okay. Well, oh, Richard just says super interesting project and great design, Rafe.
Thanks, Richard.
Thank you all so very much for coming. I hope you got lots out of it, as I did. The session has been recorded and it will be shared with you in the next 24 hours. Please do join us at the conference later in the year. We really appreciate you giving up time to come along to listen to these webinars. Nikki puts in a lot of effort into making sure that they run smoothly and we get these fantastic speakers. Yeah, it means a lot when we get a good turnout. And once again, thank you so much to our speakers and sponsors today. That was just fascinating, and I can't wait to hear the part 2 when it's finished, and we can maybe even go and see it. Thank you all so much.
Thanks.
Thank you.
Bye.